to deep dive into one project that I led specifically, but then also zoom out and give you a little bit of an overview of what robotics at FAIR is doing in general from my perspective. So I have a very particular perspective, which is more focused on generalization and adaptation. And other people would tell you other stories, so you get my story today. All right. Just to ground the discussion, I always like to start with an overview of these kind of tasks, which we humans can do all of them with some success. Some of them we have to learn, but we are very capable doing a diverse set of skills with infinitely many variations. And here, variation, I mean like different homes, different like objects. It's just the amount of generalization capabilities we have is staggering whenever I look at a robot trying to get the same. All right. And the question then I pose often is, well, how can we enable learning of these diverse set of skills in everyone's homes? How do we get there? Now, in the past, I have been much more focused on the adaptation parts, but since joining Meta, I've started to look more at, well, let's first train models that generalize as much as they can. And then let's figure out how to adapt them efficiently and autonomously once you've deployed a robot. Fundamentally, I believe we cannot prepare a robot for everything that will ever happen in the real world, but we should try to give them as much knowledge as we can before then trying to continuously adapt and make them fully autonomous from scratch is maybe really hard in a new home. Okay, so today I will focus on that generalization part. There will be a bit of adaptation, but yeah. Okay, what does generalization mean? Well, generalization comes in very many forms in robotics, and I think that's what makes it so hard. We have different home environments, or not even homes, any kind of environment. We have different tasks and skills we want the robot to learn. There are different embodiments and objects, but then there is also, for example, what I didn't put down here is we want them to eventually collaborate with humans, and humans are very different. They come in various embodiments and so on. So the axis of generalization in robotics that we have to worry about is, yeah, it's large. It's much larger than in any other problem area that I'm aware of. So before I dive into what we at Meta are doing about this problem of getting generalization, I actually wanted to get a quick sense of what you guys think is necessary to achieve this generalization. How do we get robots into our homes and be able to perform any type of task? Do you think, and I will call out all of them, but before I call them out, do you think we need more robot data? Do you think we need better architectures, or do you need better algorithms? And I want you to pick one. I don't want to answer all of them. Okay, so tell me, if you are thinking the most important part is more robot data, please raise your hand. Interesting. Okay, that's a large part. What if you think it's better architectures, please raise your hand. Okay, interesting. I hope some people are not double dipping here. If you need better algorithms, please raise your hand. Okay. It's interesting. The data access is what people seem to generally believe is the most important axis to push on right now. Maybe it's a convergence of time, like it's the right time right now to try to get more data, or because we see what large scale data can actually achieve in other fields. I personally think, obviously, I didn't make myself pick. I think it's a combination of all three, but I made you pick because I wanted to see. All right. At Meta, we have the resources to collect data, and we have a ton of compute. So I think it's probably not a surprise if I say that we are pushing very heavy on the data front. I classified this into three categories. the first one, which is passive data, you can think about image data sets and video, most importantly video data sets out there that we can use to train skills or model parts for robots. Then there is, of course, the large-scale reinforcement learning or behavior cloning and simulation, and then doing some to real transfer. And then there is the final axis that I will touch on today, which is the teleoperation data, which is becoming very big now as well. Okay, my work has been primarily in the first axis, and that's where I will do the deep dive, and then I will zoom out and talk about other projects at Meta, at FAIR in robotics specifically, that touch on these other fronts. Okay, what does it mean to utilize passive data to train diverse robot skills? Well, the first step we took at this was actually to use self-supervised pre-training of visual representations on out-of-domain video data, and use that as a strong prior before trying to train a policy on top of that, and then fine-tune, if needed, the visual representation as well for a diverse set of downstream tasks. So this looks like that. Basically, you have a first task-agnostic pre-training stage where you have some generic self-supervised signal that helps you train, let's say in this case, a visual perception model. And then you have a task-specific adaptation phase. We've seen this in computer vision, right, like classification and so on. In our case, it was control, basically. This project was started in simulation, and then we did do evaluations on hardware as well. So we called this the artificial visual cortex when we started. We had some fun naming this. Before we started with this project, we actually wanted to understand, do we already have such a general visual perception module out there? At the time we started this, other people had started looking at this already. And so we created a benchmark, which we called Cortex Bench. And it consists of 7 benchmarks, 17 tasks within those 7 benchmarks, and we are tracking 2 metrics. I'll go more into this later. And the benchmark tasks are covering different observation spaces, different action spaces, different ways of specifying the goal, and both policy learning was done either with imitation learning or reinforcement learning. And then you can also see there's some variety of the simulators that we actually tested. So there's some 3 habitat simulators and 4 Muchoku environments. We used some of the models out there that were there at the time, like MVP, Wave, Clip, and R3M. And we evaluated them on all of these tasks. And what we found is that for if you use MVP, it is best on 3 tasks. If you use R3M, it's best on 3 different tasks. And then Clip was best on 1 specific task. So there was not one model that was sort of outperforming all of them. And it is kind of expected. Just the simulation environments are very diverse, and the tasks are also very diverse. And these representations weren't pre-trained with these tasks in mind, and neither did we, but we did cover much more diverse pre-training data, which I think helped at the end. But let me get into how we trained our visual cortex model. I will go over pre-training data sets, very quickly touch on pre-training objective, and then and the model architecture. But those are the choices that we sort of explored and studied. Okay, so we used Ego4D as a base data set. So any VC1 variant we trained had always Ego4D. And then we tested what happens if we add extra manipulation video data sets, like something Epic Kitchens and 100 Day of Hands. And that allowed us to study how much does it help if we add these manipulation-focused data sets on these benchmarks. We also studied what happens if we add purely navigation data sets like Real Estate 10K and Open House. Like, I don't know if you've seen these type of data sets, but they walk through houses and so on. And then we also thought, well, let's study what happens if we add something like ImageNet, which doesn't have necessarily anything in particular to do with the tasks that we care about, but it's more data, so let's see. We used a VIT architecture and self-masked auto-encoding as a pre-training objective. And we studied what happens if we also increase the size of the encoder. So we used a VIT base and then a VIT large. All right, so here's the first takeaway. If first of all, scaling model sizes, maybe unsurprisingly, but that is still worth studying. The larger model outperformed the smaller models, and these numbers that you're seeing, these are maybe I forgot about that part. Basically, we pre-train the visual representation on these various combinations of video data sets, and then we freeze that visual representation and train policies for each task, basically using those visual representations. And the numbers you see are the performance, like how successful these policies end up being in their specific area. So the visual representations are not fine-tuned here. They are used frozen, and just the policy is trained on top of that. Okay, so larger VATs were better than smaller. Scaling the data sets, overall more data was helpful. Adding a computer vision data set like ImageNet helps, which I thought would not be the case, but I was proven wrong by my AI resident. Cross-domain diversity, and by that I mean, for example, taking both manipulation data set and navigation set into account was more important than adding many different manipulation data sets, interestingly. So that was also an interesting insight. Yeah, so unsurprisingly, I wouldn't be talking about this if our model wasn't at the end, at least at the time we did this, the best according to the benchmarks we measured performance on. We actually, because we wanted to get, so you see two types of, so first of all, you see a ranking of the models here. The top is the model that was trained on Ego4D plus manipulation plus navigation and ImageNet, and that using a VIT large, and that ended up performing the best. Now all the darker purple ones are variations that we trained as well, but they ended up not performing as well. For example, the model without ImageNet is third. And then all the other in lighter colors are baselines, whether it's other pre-trained representations or randomly, most notably the randomly initialized models that we ended up fine-tuning for the tasks. So you do see actually improvement, like a significant improvement by pre-training on these video data sets as compared to randomly fine-tuning, randomly initializing and then fine-tuning on those tasks. All right, yes?
What kind of information or knowledge in the pre-training phase, like looking at the parameters, did you see that they were able to kind of grasp?
So when we pre-trained, we didn't have any of the simulation tasks in the loop, right? So we just look at the losses, how they're converging. But what I can show you later, I took this out because I thought the talk would be too long. I can show you the features that we trained. And I think maybe I have features of different variations of these, or at least one baseline. And it's quite interesting to see the different types of features that are being learned. So that's what I use to analyze what those models, like, are those models doing well? Like, I looked at the visualizations of, I think we used something like RADCAM, which backpropagates based on the task, what activations, what is it attending to in the image, basically, and we visualize that. It's quite interesting. Yeah, remind me to bring that back, and then, yeah. Okay, the best competitor was MVP. It is very similar in the approach, but it used different data sets. And we did use a slightly different pre-training algorithm as well, but the primary difference was, I think, the pre-training data set. And then the worst performing model was CLIP for these tasks, at least. Okay, so this was the pre-training phase, and then the question was how, let me actually first show you this figure. So this is the performance we got on all the 7 tasks, where benchmarks, where in the red line you see the best possible result that the community had produced by then in any means. Like, we didn't care, we just picked whatever number was the highest we found reported. And in blue you find our recipe of pre-training on video data, and then keeping it frozen and training the policy on top of that. And you can see that on some tasks it did as well, slightly better. Some tasks it was lagging behind. And on average, it was still very impressive result to get this out of the box, this sort of zero-shot transfer of visual features for robotics. But we wanted to be the best on all of these tasks. So we thought, okay, so now it's time to do this adaptation. Can we adapt VC1, the visual features, either through end-to-end fine-tuning while we're learning the policy, or we also studied the MAE-based adaptation on in-domain data. That means we collected some additional in-domain data and fused that into the MAE pre-training and fine-tuned with MAE basically on top of the initially pre-trained. And now you see we're not still always really 100% the best, but we're basically on par or better than the prior reported numbers on these tasks with one approach, right? So yeah, I was very excited about that. Okay, we also studied this on hardware, of course, because simulation tasks are simulation tasks, and I always care about does this actually work on robots? We studied 5 different manipulation tasks and did few-shot imitation learning, because large-scale reinforcement learning isn't really a thing on hardware right now. So we did a tri-finger, and Claire helped with this. Then we did random reaching with a Franca arm. We picked up a bottle with the Franca arm. We had like a little setup of a toaster, moving the toaster button up and down, and then also opening a drawer. So those are the tasks. You see the number of demonstrations we used. They are fairly small considering what we use these days. And that's what we used to do few-shot imitation learning for policies on hardware. And then we compared this to, so these were internal benchmarks that we had. So we compared this to our best performing baselines that we had internally. And we were able to show that with VC1, we were able to outperform those internal baselines we had. Just to give you a sense of these tasks, the Franca arm, picking up the bottle. We might have included some failure in this video as well.
affected?
Yes, so we were, it's kind of an automatic task resetting mechanism. Yeah, struggled a bit with that one. Then the opening of the drawer. Pushing the cube into a goal image. Yeah, that's it. That's just a few examples. All right, if you want to learn more about this specific project, you can go and find this. We open sourced the benchmarks as well as the models. So yeah.
I have a question.
Yes.
So you had this one figure where you showed through adaptation that everything got better. How was that done? Like fine tuning or?
Yes, we did end-to-end fine-tuning, and whether it was imitation learning or reinforcement learning depended on the task, because some of these tasks were done via reinforcement learning and some were imitation learning, basically. Yeah.
Okay.
Yeah.
So just a quick follow-up on that. It was a combination of the in-domain MAE objective and the downstream task objective?
We studied both of them. I think the numbers that I showed you were with the end-to-end fine-tuning, and we also have numbers with the MAE-based adaptation only.
Thanks.
And so I think the end-to-end fine-tuning ended up working a little bit better. With interestingly, interesting tidbit about this is for the Mojoko tasks, the domain gap was actually quite large because we trained on real data. So that one were actually the hardest to close the gap. And that's also why I wanted to move to real robot tasks, because I was like, I don't want to worry about fixing the real to sim gap right now. So yeah. Okay. So what's next on this front? Because that's mostly the area I am focusing on right now. Well, this was all about just visual representation, which is all good. But you know, what about actions? Right, at the end of the day, we want to train policies or models that can help robots perform tasks in the real world. And so I particularly am interested now in world models. So I'm looking at action conditioned world models, pre-training them on data out there and getting action data in there. So yeah, if you're curious about this, please ping me, because I think about this a lot right now. Okay, so this is now where I zoom out and talk about some projects from other people in the robotics team at FAIR. So the second data hypothesis is large-scale reinforcement learning or behavior cloning in simulation. So what FAIR Robotics has worked on is the development of visually realistic simulators and benchmarks, then train and evaluate high-level reasoning policies, particularly focus on high-level reasoning so far in simulation, and then transfer that to the real world. Of course, the definition of high-level reasoning is a bit fussy, but you'll see one concrete example. Just to give you some snapshots of the simulator. So we have Habitat 2.0 here that came out in 2021. And it was all about training home robots to rearrange their habitat. So it was basically a general definition of pick and place tasks with diverse home environments, diverse objects in those home environments, and so on. That was open sourced, the simulator as well as the data sets, so the assets to generate these visually realistic scenes were all open sourced. There's also a challenge around this, so people can actually study this themselves as well. And then there was a recent follow-up on this, the Habitat 3.0, which is now focused on also getting humans in the simulation and sort of studying social rearrangement, social navigation, that's how we call it. But it's moving towards collaborating with humans, basically. Yeah.
How are the humans No actions guided?
You mean how are they modeled? There's an agent basically that represents the human. Yeah. One of the projects, so of course, when you have this hypothesis, at some point you have to show that if you're training in simulation, that actually leads to something that works in the real world. This is one of the projects of one of my collaborators, Akshara, who basically took this general purpose mobile manipulation task of I want to be able to pick and place objects from random location and random unseen objects and perform this task many times and be successful. So this is the task description that you see here. You have a robot initialized somewhere. It needs to navigate to the right place, pick the right object, and then navigate to the placing target, and then place it there, basically. So that's the task definition. There were 2 phases of training. Both of these phases are trained in simulation. Akshara decided to train some basic skills in simulation. Those were the navigation skills, the pick skill, and the place skill. And they were trained with generalization in mind. So in simulation, you basically take a bunch of different home environments and objects and then train those skills to perform the task, basically. And then there was a high-level sort of policy that does the coordination between those skills, like decides when to pick what skill. And also it sort of has an adaptation layer to adapt to any sort of disturbances at test time. I linked the project link because I don't know all the details of this project anymore. But if you're curious, please follow that link. So AAC was trained entirely within the Habitat Simulator. And there were 2 types of datasets used, HM3D dataset, which was used for the navigation training, and then the replica cut was used to train the pick, place, and coordination. And then on the right side, you actually see our Fremont apartment that we have at Meta, which we use as sort of a held out test validation set. So our real world testing suite. And you see the robot performing the tasks. There are many more videos on that link if you're curious. And yes, this is a Spot robot. Any questions about this part of the talk? Okay. I also want to highlight 2 recent benchmarks that we put out. So this is actually something that I was involved in as well, OpenEQA. So they are both, the 2 benchmarks I'll be talking about, they're both sort of using Habitat as a foundation. This is an agent that we drop an agent into a home environment, and then we ask open vocabulary questions, like what color are the blinds or what food is next, and then the agent will have to navigate to that place, or it has to do it from memory, like assuming it has been able to explore the whole space, and then answer those questions. This was the first open vocabulary benchmark dataset for EQA, which is embodied question answering. And it supports both use cases, this sort of episodic memory where you assume the robot has already explored the whole space and it can answer from memory, or the active exploration use case where it says, oh, I don't know, and now it has to figure out where to go. It contains over 1,600 high-quality human-generated questions from over 100 real-world and 180 real-world environments. And because this is a benchmark, once you have these open vocabulary questions, you actually need a way to test how well the agent is performing. We have developed an automatic language model powered evaluation protocol that shows excellent correlation with human judgment. So that is one of the benchmarks. And the other benchmark that partner team put out very recently actually is called Partner, and this is about enabling sort of this multi-agent reasoning and planning, so studying that aspect. And primarily we have in mind a robot and a human agent, basically. And the tasks are all about sort of maybe cleaning the home environment, and the robot agent has to, in our case, the way we think about it, has to adapt to, or the human is picking up the pillow on the floor, so I'll pick up something else because that's more efficient. So those kind of things. Partner comprises 100,000 natural language tasks designed to study this multi-agent reasoning and planning. It also uses LLMs to generate these tasks at scale. It exhibits characteristics of everyday tasks where you have variations in spatial, temporal constraints. Like temporal constraint could be something like something has to be done before the next part can be done. And it also enables evaluation of AI agents with real human partners through a human-in-the-loop infrastructure. Yeah, go check out those benchmarks if you're curious about these type of problems. Okay, so now I will get to the final piece, the teleoperation piece. It is actually, we are particularly focused on teleoperation for dexterous manipulation tasks. This is sort of where a lot of work still needs to be done to get really good teleoperation with also tactile sensing in the loop. So I'll actually touch on first the tactile sensing and the general models we are training for that, and then how we start using them to build teleoperation stacks for dexterous manipulation. And here the question is now, I think for dexterous manipulation, we all have this intuition that at least for us, we have this intuition that we will need this real world data. We will need this tactile feedback to actually train robust robot policies. And so that's why we're focusing the efforts on that area right now. I don't know how many of you have seen it, but we have recently had a big release of the Digit 360, which was a big collaboration across many different organizations as well. It's the latest development of this tactile sensor, which is a vision-based tactile sensor, has a silicon fingertip, hyperfisheye lens, and so on. And we actually put those on an Allegro hand. So we have an Allegro hand where each fingertip is one of those digits. And that's what we work with at Meta. What's interesting is that we have had variations of this. I mean, GelSite had the first variation of this, but then we started building on top of this. And so now we actually have a family of visual tactile sensors, and we want to be able to use the data from all of them because it is so hard to actually get that data. So the part of the team, the robotics team, studied learning general touch representations that can take in tactile images from any of these sensors, and basically trained an encoder also with self-supervised learning that can then be used for many tactile sensing tasks like force estimation, slip detection, or also policy learning at the end of the day. And so we applied this also to these different sensors, and this is super cool that we start using this encoder now for training policies or even world models. Now, on the teleoperation side, the thing that we've been working on is, so you see let me actually first show you the videos. I think that is better. So what we're aiming to do is we have a human with a glove, and we want to mimic on the robot side, that movement that the human is doing. And on this side, the left side, you saw what happens if you don't have DexGen. That's what people ended up calling it, which I will talk about in a second. And then on the right-hand side, you see how it looks like if you use the controller that was trained by our team. So this is sort of the end goal, to improve this teleoperation with tactile gloves. And the way the team went about this is, again, in two phases, where we have a pre-training stage in simulation, interestingly, where we divide, like, we have multiple tasks defined in simulation, and we train controllers for, like, we train one controller for all of these tasks. And from out of that controller comes a learned action distribution, so something that sort of maps. We basically have a distribution of all possible actions that we've trained in simulation. And then at test time now on the real robot, we take either from a policy or a teleop the desired motion that we want to accomplish, so the command, feed that into this controller, and what the controller ends up doing is projecting it into what is the safe space, basically, for the hand to perform. I don't know all the details about it, I have to admit, but it's quite interesting to see. And again, I think the results, so this was just open sourced, I think, very recently, like 2 weeks ago or so. So yeah, that is where we're heading with the teleoperation. Overall, what we are aiming to do is to put the Allegro hand on the Franca arm and the Franca arm on a mobile base, and now start collecting data for many diverse tasks. But that gives us vision, tactile sensing, and proprioception combined, and then start collecting data, and then train better and better models. That's it. That's all I have for today. If you have any questions about any of these projects, I will not maybe be able to answer all of them, but I can forward you to the relevant person, so please ping me. And also the robotics team is hiring, so please let me know if you're interested in interviewing.
Great. Question.
Yes. Any questions? Yes.
Can you share your opinion about what problems or challenges for world models?
For world models? Yes, I can share a little bit more on that front. So for world models, where I see the biggest challenge right now is actually correctly predicting object interactions. We have some very first results for reaching movements, which was impressively, we used no training data. So we used the droid data set. We took a video world model and fine-tuned that with action data from the droid data set. And that zero-shot transferred to our Franca setup for reaching tasks. But now when we try to push an object or grasp an object, we start to see the limitations of world models. So I actually think we need to get contact in those world models, so, or tactile, some tactile sensing. So that's one of the axes we're exploring. But at the same time, it's still just more data, basically, that I think we need to train better world models. Yeah.
Yeah, I have questions on what is your opinions on the bottleneck in the VLA model? Like, what is the next big thing for vision and action model?
For the vision, so the world model or a policy, like a.
Or what is next biggest bottleneck to vision language action? action?
The visual, yeah. So we're actually also looking at this right now. We don't have anything put out yet. I mean, to be honest, I feel like the generalization of these models isn't yet there where we need them. And so to me, it's understanding how can we leverage these VLMs that give us very good semantic understanding of the world and connecting it to a policy. I don't necessarily think the right way is to try to make the VLM predict an action. That doesn't feel right to me, but who knows? Someone might prove me wrong again. But I think like connecting that knowledge to the policies is how to do this effectively is a good question to study. And then I just really think we need to continue pushing on the generalization axis because we are downloading some of these models and testing them out. And what I'm seeing is not like zero-shot transfer to our setup, basically. So it's not there yet, in my opinion. But
cool. We've seen some zero-shot transfer of these models. We've seen some zero-shot.
You've seen some, yeah. Okay, so what tasks?
Pick and place, folding,
Yeah.
stacking,
Yeah.
some low precision insertion.
Interesting. Okay. Yeah. Or without any fine-tuning?
Without any fine-tuning.
Then I have
But
to...
also our just general lab is in the Droid data set, but
Yes.
just not that particular setup and that table and all of this.
So we are struggling a little bit with getting this.
That's interesting to know.
Yeah. Interesting. That's a very good question. I don't know. I think one question I have thought about a lot is this question of memory, how to represent memory, because the 3D world is a good representation to store information, basically, that you've observed, right? So you don't, you don't have to re-explore the home every time when you're trying to find an object because you have seen it probably before, and the 3D world is a good way to store that information. But I don't, tokenization for 3D representations is very, very much behind tokenization for 2D representations. So it's a good research topic to look at. For manipulation tasks, I wonder if 3D or 2D, like implicit or explicit representations are the right thing to do. So that's another thing I think a lot about, yeah.
Are there questions on Zoom?
Yes, there's one question from so how is tactile sensing used in Dextran?
It's not used yet, but it's coming up now, yeah.
What was the question? Yes. Sorry? No. No? I thought you had your hand.
Maybe related, I'm not sure if that previous question was it, but have you released any open source data sets that have tactile sensing and vision?
So I think we released a sparse data set. I'd have to quickly Google this, but I don't know if so there's a link here. I don't know if we also gave images, probably not, like RGB, I don't think so. But yeah, that's what we would be working towards.
That is in the near horizon.
Well, I don't know how near. Let's say maybe this year. I don't know. It's hard to say.
You talked about some research. I'm not sure if it was yours or somebody else at FAIR doing navigation pick and place with the Spot robot.
Yeah.
What was the 3D representation there? Or was there one?
There was no, there was actually, so there were some assumptions that were made, like you saw that the robot had a 3D location of itself, and it also knew the 3D location of the receptacles. So there was a little bit of a map there, yeah, a course map, basically.
Is that provided by the simulator itself?
It was provided by the simulator, and then in the real world, I think it was provided by manually measuring things, yeah. Yeah.
More questions?
So like, so you created some visual representation with like your visual cortex model, and how are you like translating that into robot actions for downstream tasks?
Yeah. I rushed over this. Yeah, I took that slide, and I don't even think I have it in the backup slides. So it's a little hard to say this generally because we have these very diverse tasks. But when you look at the Mujoko tasks, the Trifinger Meta World, they were done with demonstration data. So we had a set of demonstration data that we had collected, some low shot number. I don't remember the exact number. And then we did behavior cloning for those where we had demonstration data and end-to-end fine-tuned through that behavior cloning. For ImageNav, that was a large-scale reinforcement learning policy trained in simulation. So that one doesn't assume any prior information. It just takes sensory observations and trains a policy through reinforcement learning. ObjectNav is a large-scale behavior cloning dataset that we used. And the mobile pick skill is also reinforcement learning. So it depended on the task.
So for some of these tasks, like you're seeing, some improvement on some of them, and on others, sort of comparable performance. I'm wondering if, aside from sort of final performance or like success rate on these tasks, whether you saw other like ancillary benefits of pre-training these representations. Because final performance, you might be bottlenecked here by the actual task data, for example, imitation learning, but were you able to converge faster in training? Were you more sample efficient? These sorts of questions.
Yeah, we didn't. I had this intuition that it probably will help be more sample efficient. We just didn't end up studying it because for time reason. I know that in the reinforcement learning, on the reinforcement learning side, we did look at speed of convergence. And the thing is, the reason why we ended up reporting it like this is if you just give enough time to the policy, the policy starting with a randomly initialized controller, if it can catch up, that was okay with us. We just wanted to report the best number we can get. But we did definitely see faster, with the pre-trained visual model, you get to a better number faster, basically. So that initial pickup, that initial gain is faster, basically, yeah.
More questions?
So we see big gap between the generalization you showed at the first slide and the cortex bench, right? So can you think of any simulated environment or simulated bench that can bring the gap closer? What I mean is, if we have 8 instead of 7 bench over there, it will not probably be more general. But can we think of maybe one simple test that if the model shows this in simulation, it will be more generalizable for that kind of scenarios?
Sorry, are you asking, can we find that one experiment in simulation that will tell us whether it's a general?
Yeah. Maybe it will help us. Maybe.
I haven't found that yet. And worse, depending on the simulator you use, the sim-to-real transfer isn't always very clear either. So we actually did a correlation study between if we use VC1 in simulation and then transfer the policies with different parameters or different backbones to hardware, are they ranked the same? Are the hyperparameter results ranked the same in simulation as they are on hardware? So we did a test of that. And unfortunately, I can't say that there was like for all simulators a very clear signal that I can use simulation as a way to test, like pick hyperparameters that then also work the best on hardware. But for specifically the ImageNav task, which is basically you get a goal image and you navigate to that goal. You have to the agent has to navigate to that goal image. There we saw very good correlation and transfer, and it kind of makes sense because it's a mostly like basically the driving over the surfaces was abstracted away, and it's mostly a visual, like moving through space in a visual task, and the simulator was photorealistic, so the transfer was fairly good from the policy. So there the ranking was good, very well correlated, but then for other tasks the ranking wasn't very well correlated. So basically what I'm telling you is no, I'm sorry, and it's worse than just trying to find one metric. We can't even just say, oh, we have these results in simulation and they will automatically transfer to hardware. So
maybe time for one more question. Nothing on Zoom. Okay, well then let's thank the speaker again.
Yeah.
Thank you.